Right, moving on to enthalpies of solution. Just remind ourselves that the lattice enthalpy of formation is the enthalpy change when 1 mole of a solid ionic compound is formed from its gaseous ions, and here's an example equation right here. The lattice enthalpies of formation are always negative because when a lattice forms, new bonds are formed, resulting in energy being released, so an exothermic reaction. So now we've recapped that definition, it's now time to understand that lattice enthalpy values are affected by the size of the ionic radius. So the larger the ionic radius, the less exothermic, the closer to zero the lattice enthalpy will be. And the reason for that is because the attraction between the outer electrons and positive nuclei decreases as the radius increases. The second thing, the charge of the ions, the greater the charge, the more exothermic, the more negative the enthalpy of lattice formation. So let's make a few comparisons, bringing into account both the size of the ionic radius and the charge on the ions. We already said that the smaller the ionic radius and the greater the ionic charge, the more exothermic the enthalpy of lattice formation will be. And this is true here if we compare magnesium oxide with barium chloride. Remember that magnesium group 2 will have a 2+ charge, oxygens in group 6, O2-. In terms of their ionic radii, they're going to be small ions, they're highly charged, which means they have a large enthalpy of lattice formation. Barium chloride, however, barium is much lower in group 2 compared with magnesium. It has a much larger ionic radius, meaning that the barium chloride will have a smaller enthalpy of lattice formation compared with magnesium oxide. The lattice enthalpy can also be calculated theoretically using a perfect ionic model, which assumes that ions are point charges, ions are perfect spheres, and only electrostatic attractions occur between the ions. So we're making a statement that only ionic bonding occurs and that there's no covalent character. However, in reality, bonds usually have both ionic and covalent character. And actually, the Born-Haber cycles, because they're based on experimental data, they're actually more accurate because they take into account the fact that both ionic and covalent character exists within the bonds. Whereas the theoretical lattice enthalpy values are based on the perfect ionic models, and that explains why these values are often smaller than those calculated using a Born-Haber cycle. To explain this further, it's because the covalent bonds are stronger than the ionic bonds, and therefore we can make the following conclusion, which is that the closer the theoretical and experimental values, the more ionic the character of the bond. 2 more definitions now, they never end. Enthalpy of hydration, this is the enthalpy change when 1 mole of gaseous ions are converted into aqueous ions, so an aqueous solution. So there we are turning from a gas to aqueous. The enthalpy of solution is the enthalpy change when 1 mole of a solute dissolves completely in sufficient solvent to form a solution in which the molecules or ions are far enough apart not to interact with each other. When an ionic compound dissolves in water, which is a polar solvent, the positive ions of the ionic compound are surrounded by delta negative oxygens. The negative ions are, however, surrounded by delta positive hydrogens. And now we're ready to draw thermochemical cycles in order to determine the enthalpy of hydration or solution of an ion. So in this question, we're using the data in the table to construct a thermochemical cycle for the enthalpy of solution for magnesium hydroxide, and we're calculating that in kJ per mole. Before we get going on this, I just want to remind you that this lattice enthalpy of dissociation, we met it previously in the Born-Haber cycles. Remember, this cannot be determined experimentally. We need to do a number of steps in order to calculate it by going through an alternative route. So just to remind you, look, here's a Born-Haber cycle for magnesium bromide, and it's that enthalpy of lattice dissociation that we see here that we calculate by going through all these other steps involving atomization and ionization. So this remains in essence the same approach, but we're just going to look at enthalpy of solution and enthalpy of hydration. So I've pulled in the 3 key definitions here, the ones we'll constantly refer to. So the first thing we want to do is set ourselves up for the lattice enthalpy of dissociation. Remember, it's when 1 mole of solid ionic compound separates into its gaseous ions. So at the bottom, I'm going to show the solid compound, 1 mole. So let's separate it into its gaseous ions. So remember, Mg is in group 2, so it will form Mg2+ ions. It's gaseous. Will form 2 hydroxide ions with the OH- charge. And remember, this is your enthalpy of lattice dissociation. Now we need to include these other definitions. So the enthalpy of hydration, so we are turning these into aqueous ions effectively. So the enthalpy of hydration is when 1 mole of gaseous ions, which we have, are converted into aqueous ions. And remember, we do this one step at a time. So let's take the Mg2 plus, turn it into aqueous ions, keep the hydroxide the same, label this. So enthalpy of hydration of the magnesium ions. Let's get our hydroxide ions into aqueous solution. Label that line. And then our final step is to go from aqueous ions to the solid. Check your definitions again. Enthalpy of solution is the enthalpy change when 1 mole of a solute dissolves completely in sufficient solvent to form a solution in which the molecules or ions are far enough apart to not interact with each other. In other words, you have dissolved the solid, and that's why this particular arrow will go in this direction, showing that that solid has been dissolved. So this is how you'd set up your cycle for enthalpies of solution. Obviously the question varies in terms of where your X value will be. Here we're being asked to find the enthalpy of solution, which means that it's actually this one here that's the X value. Sub in the rest of your numbers using the table. There's your start and end labels. So acknowledge the arrowheads as you go around. So that's in the same direction. So it's 2842 minus 1920. Just be a little bit careful here. Look, we have 2 hydroxide ions. So we do 2 lots of minus 460 because there's 2 hydroxide ions being formed in aqueous solution. Put that into your calculator. So that gives us a final answer for our enthalpy of solution of 2 kJ per mole. Just a few extra things to point out. The enthalpy of hydration value is affected by the ion's radius and charge. This means that as the ion's radius increases, the enthalpy of hydration decreases. It becomes less exothermic. For positive ions, so positive cations, this is because as the ionic radius increases, the force of attraction between the metal ion and the delta negative oxygen of water decreases. For negative ions, negative anions, this is because as the ionic radius increases, the attraction between the non-metal ion and the delta positive hydrogen of water decreases. And then lastly, as the ionic charge increases, the enthalpy of hydration increases, becomes more exothermic. The greater the charge to size ratio of an ion, the stronger the attraction to the delta negative oxygen and delta positive hydrogen of water. So for example, the hydration enthalpy of magnesium ions, Mg2+, is more exothermic than for the sodium ion because the magnesium ion is smaller and more highly charged, meaning that it attracts the delta negative oxygen of water more strongly. So let's look at a past paper question. When magnesium chloride dissolves in water, the enthalpy of solution is minus 155. The enthalpy of hydration is minus 364. Calculate the enthalpy of hydration of magnesium ions. We've been given lattice dissociation enthalpies for these substances. So we'll start with our solid magnesium chloride at the bottom. Now we'll do a lattice dissociation enthalpy for that magnesium chloride. So we know we're going to form magnesium ions and chloride ions. Add my arrow, get it labelled. Now we need to get the magnesium ions and chloride ions into aqueous solutions. So let's start with the magnesium. We only change one thing at a time. Get that labelled. That will be your enthalpy of hydration. And that's actually our X value here. That's what we're being asked to find. Now, I know automatically you probably want to hydrate your chloride ions and turn them into aqueous ions, but just be a little bit careful here. We've been told that the enthalpy of solution is minus 155. That minus is important. Remember, enthalpy of solutions is all about dissolving your solid and forming your aqueous ions. So because it's minus 155, you actually need to draw your aqueous ions lower than the solid magnesium chloride. So that there is minus 155. So you're now finally ready to do your hydration of chloride ions. Just drawing an arrow down here. So that's your enthalpy of hydration of chloride ions, which we know is -364. You're almost ready. Add a start here, end here, and then just follow this route in this direction, making sure you acknowledge the arrowheads. So x equals, that arrowhead is going against, so we need to do -2493. This is going in the same direction, so it's -155. This is going against the arrowhead. Take care, remember you're forming 2 chloride ions, so we need to actually multiply that -364 by 2. So your final answer will be -1920 kJ per mole.